Another centripetal motion question. This one's meant to mimic what you did in the lab or what you simulated in the lab this year. It's not perfect. A string will never be completely horizontal, but we're going to pretend that it is. And once I'm done it, I'll show you how things would change in the real world when the string can't be horizontal. So kind of like you saw in the lab, we've got this rubber stopper flying in a horizontal circle. The string is, the numbers I made up, 1.4 meters long. Rubber stopper's on the end. It's got a mass of 50 grams when we need it. We're assuming that the string is horizontal. That means gravity is straight down, perpendicular to the direction of the acceleration, so I don't really need to worry about that. And the tension, strings can only pull, so the tension is back along the length of the string. Circles always turn into an F net equals ma situation. In this case, we don't worry about gravity because it's perpendicular to the acceleration. We're assuming the string is perfectly horizontal. So the only force making it go in a circle is the tension. The full tension, since it's completely horizontal in our assumption. So we get tension equals mv squared over r. For the numbers I made up, the tension was 2, the mass was 50 grams. We've got to put that in kilograms. Don't know the v squared. And the r was 1.4. Flipping things around, doing some algebra, I get that the speed is 7.5 meters per second. Depending how that 2 newtons is worded, that's the fastest we can spin the rubber stopper. If it goes any faster than 7.5, then we're needing a tension higher than 2, and that would cause the string to break. The way that it says the string can withstand a tension of 2, we're okay at 7.5, but as soon as we go a little bit faster, then the string can't handle that and the string will break. I'm going to quickly show you, I won't do all the math of it, but realistically what would happen? The rubber stopper would go in a horizontal circle, but the string would have to be held a little bit higher than the plane of the circle. The tension would be on an uphill angle. Gravity would still be straight down. When we talked about forces before, whenever there's a force on a funny angle, you have to get the components of it. We've got to split tension into 2. There's a horizontal component that's causing it to go in its circle, and there's a vertical component. The vertical component, so Ft vertical, that's what's actually fighting gravity. So the string's doing 2 things. Making it go in a circle, that's the horizontal part, and some of tension is fighting gravity. So if we needed to crank this out, the Ft vertical is what's canceling gravity. From that, if we know the mass, we get a number for gravity, we could get a number for Ft vertical. We knew the way this one was set up that the tension was 2 newtons. There's enough there that we could find the angle. From the angle or Pythagorean theorem, we could find the horizontal component. That's what we would plug in as our F net. Now another little wrinkle is the string was 1.4 meters long, but in this case, when the string's on a funny angle, the radius of the circle isn't going to be 1.4. The radius of the circle, we'd have to use trig, we'd have to use the angle that we've calculated to figure out the radius of the actual circle. It'll be a little bit smaller than the 1.4 that we used before when the string was horizontal. 1.4 is the hypotenuse, so we're going to have a smaller radius. For fun, if you want, you can doodle it, just a little bit of trig. You're going to get a number similar to 7.5. If my memory's correct, it's a little bit smaller than 7.5.